A binary tree is a kind of data structure where each element, called a node, can have up to two nodes connected to it. They hold some kind of information, like a number or a word, which we call the key of the node. The root of a binary tree is the very first node at the top of the tree. Edges connect two nodes in a binary tree, showing the link between a parent node and its child node. Sibling nodes share the same parent and they can be referred to as the left child and the right child. A leaf node is a node at the end of a binary tree that doesn't have any children. On the other hand, an internal node has at least one child. A subtree is a section of a binary tree that starts from a specific node and includes that node along with all of its children, grandchildren, and so on. A path is a sequence of connected nodes from one node to another in that tree. The depth of a node is the number of edges along the path from the root of the tree to that node. For example, here the node with the key of 4 has a depth of 2. The root node always has a depth of 0. The height is the number of edges from the root of the tree to the deepest leaf node in that tree. This tree has a height of 3. The diameter or width of a tree is the number of nodes on the longest path between any two leaf nodes. This tree has a diameter of 5. A full binary tree is a tree where every node has either 0 or exactly 2 children. So this can either look like a root node with 2 children, where each child is the root of its own full binary subtree, or it can just be a single node. A perfect binary tree is one where all of the internal nodes have exactly 2 children, and all the leaf nodes are on the same level. A complete binary tree is similar, but slightly more flexible. All levels are fully filled, except possibly the last, and in that last level, the nodes are placed as far to the left as possible. There's also something called an infinite complete binary tree. It has infinitely many levels, and at each level, the number of nodes doubles. Even though the tree goes on forever, we can still count the levels using natural numbers. So the number of levels is countably infinite, with cardinality denoted by aleph null. However, the number of distinct infinite paths you can take from the root by choosing left or right at each level is uncountably infinite. In other words, there are more possible paths through this tree than there are natural numbers. This cardinality is denoted by 2 to the power of aleph null, which is the same as the cardinality of the real numbers, also known as the continuum. A balanced binary tree is one where the left and right subtrees of every node differs in height by at most 1. In this example, the left and right subtrees of node 1 both have a height of 2. A single node has height 0, so the left subtree of node 2 has height 0, and the right subtree has height 1. The left subtree of node 5 is null. The height of a null tree is sometimes taken to be 0, but more often the convention is that a null tree has height -1, and a single node has height 0, so the subtrees of node 5 are balanced. The subtrees of node 3 both have height 1. The subtrees of node 6 have heights 0 and -1, and the subtrees of node 7 both have height 0. Leaf nodes 4, 8, 9, 10, and 11 are all trivially balanced. A degenerate binary tree is a tree where each internal node has only one child, either a left child or a right child. A degenerate tree is essentially just a linked list. And a skewed binary tree is a special type of degenerate tree where all the nodes lean in one direction. If every node has only a left child, it's called a left-skewed tree. And if every node only has a right child, it's called a right-skewed tree. Now that we have seen the different structural types of binary trees, like full, perfect, complete, and so on, it helps to step back and look at how these categories relate to each other. Some of these categories are nested. For example, every perfect binary tree is also full and balanced. But not every full tree is perfect, and not every balanced tree is full. It is also possible to have a full tree that is not balanced. This tree is full but unbalanced since the left subtree of node 1 has a height of 0 and the right subtree has height 2. This tree, on the other hand, is balanced but not full since node 5 has one child. In creating this table, I chose to ignore the trivial edge cases such as a binary tree that consists of a single node, since these tend to blur the more meaningful distinctions between tree types. A binary tree with n nodes has n-1 edges. This is because every node, except the root, connects to the tree with exactly one edge. For example, this tree with 15 nodes has 14 edges. A binary tree with n nodes has n+1 null links. To see why, note that each node has two child pointers, essentially places where it can store a reference to a left or right child, even if no child exists. That gives a total of 2 n pointers. Since a tree with n nodes has n-1 edges, the remaining n+1 pointers must be null. And in this example, we have 6 nodes and 7 null links. The maximum number of nodes on level L is 2 raised to the power of L. This is because each node can have up to 2 children, so the number of nodes doubles at each level as you move down the tree. This property is easy enough to see in this example, where we have a perfect binary tree of height 3. The number of nodes in a perfect binary tree is 1 less than 2 to the power of h plus 1, and the number of leaves is n+1 over 2. For example, we have seen that a perfect tree of height 3 has 15 nodes. To see how the equation works, recall that each level of a perfect tree will have 2 to the power of L nodes. So the total number of nodes can be written as 2 to the 0 plus 2 to the 1 plus 2 to the 2, and so on until 2 to the h, which can be written in summation form. This is a geometric series, and the familiar formula simplifies to give a total of 1 less than 2 to the power of h plus 1 nodes. Our perfect tree has a leaf count of 15 plus 1 over 2, which is 8. A more intuitive expression for the number of leaves is 2 to the power of h, and we find these two expressions are equal using our previous expression for n in terms of h. And finally, these are the expressions for the minimum and maximum height of a binary tree with n nodes. For example, this tree has the minimum height for a binary tree with 6 nodes. To get a minimum height, the tree should be balanced and as close to complete or perfect as possible. Recall that in a perfect binary tree, the number of nodes in terms of h is 1 less than 2 to the power of h plus 1. So this is the maximum number of nodes given height h. If we allow our tree to be imperfect, it can have fewer nodes than this. With a bit of manipulation, we get that the height is greater than or equal to the log base 2 of n plus 1 minus 1, and using the ceiling function gives the exact value for the minimum height given n nodes. And this degenerate tree has the maximum height of a binary tree with 6 nodes. This is not a complete list of the properties of binary trees, but I chose the ones I found to be the most interesting and informative. In real-world applications of binary trees, we may see patterns of numbers and other data types that look quite different than what I have shown so far. For example, we could have trees with any range of numbers in any order, and we can have trees with letters instead of numbers, or we could have trees where the keys are words. To better understand how binary trees manipulate data, we should first look at some common operations on binary trees. Inserting a node into a binary tree means deciding where to place it, either as a left child or right child of some existing node. In this example, node 4 is a leaf node, and we insert a new node as its right child by updating node 4's right pointer. Inserting a node gets a little more interesting when the parent node already has a child in that position. Suppose we want to insert a node in between node 3 and its child 6. We update node 3's pointer so it now points to the new node 8, and node 8 takes over as the parent of node 6. Deleting a node works in a similar manner. Say we want to delete node 7. All we do is set the right child pointer of node 4 to null. We can also delete nodes that have one child, such as node 8. In that case, we simply bypass node 8 by setting node 3 to be the parent of node 6. However, deleting a node with two children, such as node 2, is more complicated and requires additional logic. We'll see how certain functional tree types, like binary search trees, handle this in the next section. There are also different ways to move through a binary tree called traversals, which help us visit or process each node in a specific order. The pre-order traversal visits the current node first, then it recursively traverses the left subtree of that node, and then it recursively traverses the right subtree of that node. We always start at the root, so here the current node is node 1. We traverse the left subtree and visit node 2. Now that node 2 is the current node, we visit its left and right subtrees. The left subtree is null, so we move on to the right subtree and visit 4. We have now visited both subtrees of node 2, so we move on to the right subtree of node 1, starting at node 3. From there, we go to the left child, node 5, and node 5 has no left child, so we go to its right child, node 7. After visiting node 7, we return to node 3 and visit its right child, node 6. Another important traversal is n-order traversal, where we recursively traverse the left subtree first, then visit the current node, and finally recursively traverse the right subtree. When we start the traversal, the current node is the root node, node 1, and we first go down its left subtree to node 2. From node 2, we again go left, but since there's no left child, we visit node 2 itself. Then we go to its right child, node 4, and visit it. At this point, we have finished both subtrees of node 2, so we return to node 1 and visit that node. Now we move to the right subtree of node 1, which is rooted at node 3. And from node 3, we go left to node 5. Node 5 has no left child, so we visit node 5, then go to node 5's right child and visit node 7. We return to node 3, visit this node, and finally we visit its right child, node 6. The post-order traversal visits the left subtree first, then the right subtree, and the current node last. So we only visit a node after we have visited everything below it. Starting at the root, node 1, we move to its left child, node 2, and from there we try to go left, but there's nothing there, so we go to the right child, node 4, and node 4 has no children, so we visit this node. Then we return to node 2 and visit that node as well. Now we go back up and move to the right subtree of node 1, which starts at node 3. We go left to node 5, and then right again to node 7. Node 7 is a leaf node, so we visit that node. And we have now traversed both subtrees of node 5, so we can visit that node as well. We return to node 3 and visit its right child, node 6. At this point, we have traversed both subtrees of node 3, so we visit node 3. Finally, with both subtrees of node 1 completed, we visit the root node, node 1. The three traversal types we just covered, pre-order, in-order, and post-order, are all specific examples of depth-first traversal. They each follow the same principle of exploring a branch as deeply as possible before backtracking, but they differ in when the current node is processed. On the other hand, breadth-first traversal visits every node level by level, starting from the root. So we visit the root node at level 0, and then we move to level 1, where we visit all the nodes at that level from left to right. Then we go down to level 2, and again visit nodes from left to right. Finally, we visit level 3, where we have just node 7. Now that we have seen how trees are structured and traversed, let's look at the different functional types of binary trees. The types of binary trees we have considered so far, such as complete, balanced, and perfect, are all concerned with the structure of the tree, not the behavior of the data. But there are several functional types of binary trees that dictate the behavior of data. In a binary search tree, the left subtree of any node contains only values less than that node, and the right subtree contains only values greater than that node. So for example, this tree fits the definition of a binary search tree. Binary search trees allow us to efficiently search for a value by narrowing down the possible locations at each step, roughly halving the remaining search space each time as long as the tree is balanced. Say we want to find node 7 in this tree. We start from the root, and if the value is less than the root, we search the left subtree, and if it's greater, we search the right subtree. 7 is less than 8, so we go left, and now 7 is greater than 4, so we go right. 7 is greater than 6, so we go right again, and we have found the node. Binary search trees allow us to efficiently insert values. Given this example, say we want to insert the number 21. 21 is less than the root, greater than 13, and less than 48, so we insert 21 as the left child of 48. A new value is always inserted into a binary search tree as a leaf node. Deleting node 21 is then quite simple. However, deleting a node with 2 children, such as 13, is a bit more complicated. The in-order successor of node 13, or the node we would visit immediately after it during an in-order traversal of the tree, is 48. We replace 13 with its in-order successor, 48, and then delete the original leaf node containing 48. When a binary tree is balanced, such as this one, each operation, whether it's search, insertion, or deletion, takes logarithmic time. That means the number of steps required grows very slowly as the number of nodes increases. However, Binary search trees can become unbalanced, like in this example. Here, the search time is on the order of n instead of log n. These unbalanced binary search trees can be balanced using rotations. We first perform a left rotation around 20, which promotes 25 as the child of 12. This rotation improves the balance and reduces the height of the tree. We could further improve the balance by left rotating around 12, which promotes 25 as the root node. An AVL tree is a binary search tree that keeps itself balanced after insertions and deletions by using tree rotations whenever the height difference between subtrees becomes too large. In an AVL tree, the height difference between the left and right subtrees of any node must be at most 1. This is known as the balance factor, and it ensures that the tree stays approximately balanced at all times. If an insertion or deletion causes the balance factor to go outside the allowed range, the tree automatically performs a rotation to restore balance. For example, if we start with just a root node 20 and insert node 10, the tree is still balanced. However, upon inserting 15, the tree becomes unbalanced. Specifically, this is called a left-right imbalance because the problem node is the right child of a left subtree. A simple rotation won't fix this, so the AVL performs a double rotation. First, a left rotation around 10, followed by a right rotation around 20. A red-black tree is another example of a self-balancing binary search tree, and it uses red and black coloring rules to keep the tree approximately balanced at all times. Every node is colored either red or black, and the root node is always black. Red nodes cannot have red children, but black nodes can have black children. Every path from a node to any of its descendant leaves must contain the same number of black nodes. Or in other words, no matter which way you go from a node to a null child, you'll always pass through the same number of black nodes. And all null nodes are treated as black. For example, the tree on the right is a valid red-black tree as it satisfies all of these properties, whereas the tree on the left is not because node 3 is a red node with a red child, and the black property is not satisfied as well. Red-black trees keep themselves balanced during insertions and deletions by using a combination of color flips and tree rotations. These operations are triggered automatically whenever one of the red-black properties is violated. So upon inserting the red 1 node, the node might automatically turn black, giving a valid red-black tree. While red-black trees maintain a time complexity on the order of log n, they are not always perfectly balanced. For example, this is a valid red-black tree, even though the root node has a balance factor of 2. A Splay tree is a binary search tree that brings recently accessed elements to the top using rotations, a process known as splaying. The idea is that elements accessed recently are likely to be accessed again soon, so by moving them closer to the root, future operations can be faster. Accessing a node refers to searching, inserting, or deleting that node, but when a node is deleted, of course, we cannot splay that node, rather we splay the node that took its place. Before looking at an example, I want to mention that rotations in a binary search tree can be a bit more complex than just a left or right rotation around a single node. These 6 rotations are used in splay trees to bring the accessed node closer to the root while also preserving the binary search property. Consider this example and say we just accessed node 12. The Splay tree will perform a zig rotation, moving all nodes one position to the right from their current position. This makes 12 the root node of the tree, and the structure adjusts to preserve the binary search property. A binary heap is a complete binary tree where each parent node is either greater than or less than its children, depending on whether it's a max heap or a min heap. They're often used to implement priority queues where the maximum or minimum element can be accessed quickly. These two trees are examples of valid min and max heaps. Inserting and deleting nodes both involve restoring the heap property by moving nodes up or down the tree. Say we want to add the number 100 to this max heap. We start by inserting the node into the leftmost position at the bottom level of the tree. However, the heap property is violated because 100 is greater than 34, so we swap nodes 34 and 100. And then, after one more swap, we once again have a valid binary heap. A Cartesian tree is a binary tree that is constructed from an array of values in such a way that it satisfies the min or max heap property while also maintaining the exact left to right order of those values when the tree is traversed in order. In other words, if you perform an in-order traversal, visiting the left subtree, then the current node, then the right subtree, you'll see the values in the same order they appeared in the array. For example, say we want to make a Cartesian tree from the given array of numbers. This tree satisfies the max heap property, and the nodes appear in the same order as the original array when traversed in order. And this Cartesian tree satisfies the min heap property for the given array. A Treap is a randomized binary tree that maintains max or min heap properties using randomly assigned priorities, as well as binary search tree ordering based on node values. A priority is a number assigned to each key to help determine the node's position in the heap structure. In this example, the black numbers are keys, and the blue numbers are randomly assigned priorities. This is a valid Treap because the keys follow the binary search tree property and the priorities follow the max heap property. Say we want to insert 950 into the tree. We place it according to the binary search property, and the node is assigned a random priority. These priorities are typically assigned from a uniform distribution to ensure that the tree height remains on the order of log n. At this point, the heap property is violated, so the structure is no longer a valid Treap, but if we perform a left rotation around 900, the heap property is restored, and the result is once again a valid Treap. A threaded binary tree replaces null child pointers with links to n-order predecessor or successor nodes. They are not inherently binary search trees, but binary search trees can be implemented as threaded trees. This is a single-threaded binary tree. In a standard binary tree, null pointers typically indicate missing left or right children. A single-threaded binary tree replaces some of these null pointers with links to the node's n-order successor. That means when performing an n-order traversal, we can follow these threads directly to the next node without needing a stack or a recursion. We don't need to rely on extra memory to keep track of where we are in the tree, or write a function that calls itself to explore each branch. And this is a double-threaded binary tree. The red threads still represent right child pointers that link to n-order successors, while the blue threads represent left child pointers that link to n-order predecessors. These predecessor threads are helpful not just for reverse n-order traversal, but also for post-order traversal. The added links can also speed up access to a node's ancestors, making some tree operations more efficient. A segment tree is a binary tree that allows efficient queries and updates over intervals of an array. Each node in the tree represents a specific range or segment of the array and stores a summary of that range. such as the sum, minimum, maximum, greatest common divisor, and least common multiple. This structure allows both querying and updating ranges in logarithmic time, making it far more efficient than scanning the array each time. Say we have been given this array of numbers. We can construct a segment tree that allows us to efficiently compute the sum of any range within the array. And this segment tree tells us the least common multiple over each range. A Huffman tree is a binary tree that assigns variable length binary codes to symbols based on their frequency for optimal compression. This kind of compression is called lossless, meaning no information is lost when encoding or decoding the data. The term symbol means any unit we want to compress, like a character, word, or number. More frequent symbols get shorter binary codes, while less frequent symbols get longer codes, which minimizes the total size of the encoded data. To build a Huffman tree, we treat each symbol as a leaf node and repeatedly combine the two lowest frequency nodes, working upward to create the full tree. The path from the root node to a leaf node then defines the binary code for each symbol. Let's take a look at an example. Our symbols are letters of the alphabet, and they are each associated with a certain frequency. We first create a node from each letter and its frequency. We then place the nodes in a priority queue, ordered by their frequency from least to greatest. We remove the two nodes with the lowest frequency from the queue and join them in a tree where the frequency of the root is the sum of the frequencies of the two nodes. We then place this tree back into the priority queue according to the frequency of its root node. The process is then repeated until all of the partial Huffman trees are combined into one tree. Once the final tree is built, we assign binary codes by traversing it. Starting at the root, we assign a 0 every time we go left, and a 1 every time we go right. When we reach a leaf node, the full path from root to leaf becomes the binary code for that symbol. These codes are called prefix codes, meaning no code is a prefix of another. That's what makes Huffman coding unambiguous. The decoder always knows where one code ends and another begins. And finally, a random binary tree typically refers to a binary tree generated according to a probability distribution over all possible tree shapes with a given number of nodes. The term can also describe a binary tree formed by inserting nodes in arbitrary order without strict balancing or ordering rules. The topic of binary trees is quite vast and complex, so of course I couldn't cover all the details in this video. I wanted to include examples of applications of binary trees, but this video is already quite long, so I may just make another video on that. Thanks for watching.